This is the second part of Isro-Vssc Technical Assistant Electrical Engineering previous year question paper with a detailed solution. The exam held in 2017. Up to question number 20 we discussed in the last video. 21. A 50 Hz 4-pole 500 megavolt ampere 22 kilovolt turbo generator is delivering rated megavolt ampere at a power factor of 0.8. Suddenly a fault occurs reducing the electric power output by 40%. Neglect the losses and assume constant power input to the shaft. The accelerating torque in the generator at the time of fault is, answer is option B, 1.018 meganewton meter. Given F equal to 50 Hz and P equal to 4, we know accelerating power PA equal to PM minus PE and accelerating torque TA equal to PA divided by WS. Where synchronous speed radian per second which is equal to WS equal to 2 pi ns by 16, where PM is the mechanical input power, PE is the electrical output power, P is the number of poles and F is the supply frequency. Before fault, PE equal to PM which is equal to 500 megavolt ampere into cos phi. Substituting those values we get PE equal to PM equal to 400 megavolt watt. After fault, PM remains same while PE reduces by 40%. So electrical output at the time of fault is PE dash equal to 1 minus 0.4 into PE. That is 0.6 into 400 megawatt. We get 240 megawatt. Then accelerating power at the time of fault is substitute in equation 1 we get PA dash equal to PM minus PE dash. That is 400 minus 240 we get 160 megawatt. Synchronous speed NS equal to 120 F by P which is equal to 120 into 50 by 4 that is 1500 RPM. Substitute the values of NS in equation 3 we get WS equal to 2 pi into 1500 divided by 60 we get WS as 157 radian per second. Hence accelerating torque, substituting in equation 2 we get TA equal to 160 into 10 raised to 6 divided by 157. We get accelerating torque as 1.018 into 10 raised to 6 Newton meter. A hydraulic turbine having rated speed of 250 rpm is connected to a synchronous generator in order to produce power at 50 Hz. The number of poles required in the generator is, answer is option D, 24. Given NS is 250 rpm, F is 50 Hz. When hydraulic turbine is connected to a synchronous generator, then both running at same speed, NS equal to 120 F by P. Therefore, P equal to 120 F by NS. Substituting the value of F and NS, we get number of poles as 24. A moving coil of a meter has 100 turns and a length and a depth of 10 mm and 20 mm respectively. It is positioned in a uniform radial flux density of 200 milliturn. The coil carries a current of 50 milliampere. The torque on the coil is, answer option A, 200 micronewton meter. In PMMC meter, deflecting torque TD equal to BINA, where B is the magnetic flux density, I is the current, N is the number of turns and A is the area of cross section. Given B is 200 into 10 raised to minus 3, I equal to 50 into 10 raised to minus 3, N equal to 100 and A is 10 into 10 raised to minus 3 into 20 into 10 raised to minus 3. Substituting those values in equation of TD, we get TD as 200 micronewton meter. Question number 24. A single-phase fully controlled full-wave rectifier is driving a separately excited DC motor. The DC motor has a back EMF constant of 0.5 volt per RPM. The armature current is 5 ampere without any ripple. The armature resistance is 2 ohm. The converter is working from 240 volt single-phase AC source with a firing angle of 60 degree in both half cycles. Under this operating condition, the speed of the motor is, answer is option B, 196.09 rpm. Average output voltage of fully controlled wave rectifier is V average equal to 2 Vm by pi cos alpha. Is question 1, and V average equal to E plus IARA. We know that Vm equal to root 2 Vrms and E equal to K and phi n. where Vm is the peak or maximum voltage, alpha is the firing angle, E is the back EMF, Ia is the armature current, Ra is the armature resistance, Kn phi is the back EMF constant, N is the speed in RPM, Vrms equal to RMS output voltage. Given alpha equal to 60 degree, Ia equal to 5 ampere, Kn phi equal to 0.5 volt per RPM, Vrms equal to 240 volt. Average output voltage, substitute in equation 1 we get V average as 108.038 volt, 108.038 volt. Back EMF of separately excited DC motor. Substitute in equation 2 we get E equal to V average minus IARA. Substituting those values we get back EMF E equal to 98.038 volt. Speed of separately excited DC motor. Substitute in equation 3 we get N equal to 196.076 RPM. Question number 25. For an induction motor operating at a slip S, the ratio of gross power output to the air gap power is equal to, answer is option B, 1 minus S. Rotor input or air gap power P in equal to 3I2 square R2 by S. Rotor copper loss PCU equal to S into P in, which is equal to 3 into I2 square R2. Gross mechanical power output PG equal to P in minus PCU. That is 3I2 square R2 by S minus 3I2 square R2, which we will get, that is taking 3I2 square R2 common outside, 3I2 square R2 into 1 minus S by S. The relation between the rotor air gap power, rotor copper loss and gross mechanical power output P in is to PCU is to PG. That is 3I2 square R2 by S is to 3I2 square R2 into 3I2 square R2 into 1 minus S by S. That is 1 by S is to 1 minus S by S. Multiplying all the terms with S, we get 1 is to S is to 1 minus S. 26. A three-phase diode bridge rectifier is fed from 400 volt RMS, 50 Hz, three-phase AC source. If the load is purely resistive, then peak instantaneous output voltage is equal to, answer is option B, 400 root 2 volt. Given Vrms equal to 400 volt. As the load is resistive, the peak instantaneous output voltage Vm equal to root 2 Vrms. That we get, substituting the value of Vrms, we get Vm as 400 root 2 volt. Question number 27. A 50 kilowatt DC shunt motor is loaded to draw rated armature current at any given speed. When driven at 1.5 times the rated speed by field control, the output power delivered by the motor is approximately, answer is option B, 50 kilowatt. The given shunt motor is driven at 1.5 times of the base speed or a rated speed by using field control. In this condition, it behaves as constant power and variable torque drive. Hence, the output power delivered by the motor is 50 kilowatt. In 2 wattmeter method, to measure the power, the wattmeter readings are 10.5 kilowatt and minus 2.5 kilowatt. The total power and power factor are, answer is option D, 8 kilowatt and 0.334. Given wattmeter reading 1 equal to W1 equal to 10.5 kilowatt, wattmeter reading 2, W2 equal to minus 2.5 kilowatt. In 2 wattmeter method, the total power P equal to W1 plus W2. Substituting the values of W1 and W2, the total power we get as 8 kilowatt. The power factor can be calculated as cos phi equal to cos of tan inverse root 3 W1 minus W2 divided by W1 plus W2. Substituting the values of W1 and W2 in this power factor equation, we get cos phi as 0.334. Question number 29. Figure shows a step-down chopper switched at 1 kHz with a duty ratio of 0.5. The peak-to-peak ripple in the load current is close to, answer is option C, 0.125 ampere. Given duty ratio alpha equal to 0.5, L is 200 millihenry, F is 1 kilohertz. Supply voltage Vs equal to 100 volt. Inductance L equal to 200 into 10 raised to minus 3. Average output voltage V0 equal to alpha Vs. Substituting the values of alpha and Vs, we get it is average output voltage as 50 volt. Total time period T equal to 1 by F. Substituting the values of F, we get total time period as 1 by 1000. T on equal to alpha T and T off equal to 1 minus alpha T. Therefore, T on equal to 0.5 into 1 by 1000, which is equal to 0.5 into 10 raised to minus 3. The peak-to-peak value of ripple current I0 equal to T on into Vs minus V0 divided by L. Substituting the values of T on, Vs and V0 and L, we get the peak-to-peak value of ripple current I0 as 0.125 ampere. Note: maximum value of ripple current is inversely proportional to chopping frequency and the circuit impedance. For the better performance of the load, the conduction to be continuous. It is preferable to have less value of the current ripple or more uniform output current. The chopping frequency is to be high. It is possible to by employing the smaller values of time period. Question number 30. An electric motor developing a starting torque of 15 Newton meter starts with a low torque of 7 Newton meter on its shaft. If the acceleration at start is 2 radian per second square, the moment of inertia of the system is, neglecting viscous and Coulomb friction. Answer is option C, 4 kg meter square. Accelerating torque in an electric motor TA equal to Tm minus Te and Ta equal to J alpha, where Tm is electrical or starting torque, mechanical or starting torque, Te is the electrical or load torque, J is moment of inertia, alpha is the angular acceleration. In the question they given, Tm is 15 Newton meter, Te is 7 Newton meter, alpha is 2 radian per second. Substituting those in those equations, we get Ta as 8 nanometer and moment of inertia J as 4 kg meter square. Question number 31. In transformer, which of the following statement is valid? Answer is option D. In an open circuit test, current is drawn at low power factor. Open circuit test. It is done by keeping one of the windings open without load. Usually, high voltage winding is open and applying rated voltage to other winding, usually low voltage winding, because it is easier to apply rated voltage. The current drawn from this terminal is the no load current as a low power factor corresponding to the core loss component. Since the no load current is very small, it does not contribute to the copper loss. Core loss is calculated by multiplying the applying voltage and no load current. As the secondary side is open, the entire coil will be purely inductive in nature. So the power will be lagging due to the inductive property of the circuit. So low power factor wattmeter is used in open circuit test of transformer. It is used to find the core loss of the transformer, the no load current, equivalent resistance referred to the metering side. Short circuit test, it is done by shorting one of the winding terminals, usually low voltage terminal, and applying a small voltage across the other winding terminals, high voltage terminal, because the current in high voltage terminal will be less and easy to handle. And using a wattmeter to measure the power dissipated in the low voltage terminal. The wattmeter will indicate the full load copper loss. In short circuit test, as secondary winding of the transformer is short circuited, as the secondary side is short circuited, the entire coil will be purely resistive in nature. So the power factor will be high or unity. A short circuit test is done to find the full load copper loss and short circuit current. Question number 32. For a single phase induction motor with a capacitor start, which of the following statement is valid? Answer is option B. The direction of rotation can be changed by reversing the main winding terminals. For a single phase capacitor start induction motor, the direction of rotation can be changed by reversing main field terminals but not supply terminals. For this motor, starting performance is good, but efficiency and power factor are poor. The single-phase induction motor is not self-starting, hence it requires an equipment to start the motor. To start a single-phase induction motor, the capacitor is connected in series with auxiliary winding used to generate a phase difference between the torques, which are generated by fluxes equal in magnitude but opposite in direction. The starting capacitor is short time rated. It is of electrolytic type. A large amount of current is required to obtain the starting torque. Hence, the value of capacitive reactance should be low in the starting winding. Question number 33. An energy meter converted to an immersion heater resistive operating on an AC 230 volt 50 Hz single phase source reads 2.3 kilowatt hour in 1 hour. The heater is removed from the supply and now connected to a 400 volt peak to peak square wave of source of 150 Hz. The power in kilowatt dissipated by the heater will be, answer is option B, 1.739. For a square waveform, peak value equal to RMS value equal to average value. Peak to peak value equal to 2 into peak value. 2.3 units for 1 hour at a 230 volt energy consumed equal to kilowatt hour. That is 2.3 into 10 raised to 3 equal to V square by R into T. Therefore, from this line we get the value of R. By rearranging, we get 23 ohm. Therefore, P equal to V square by R. Substituting the value of V and R, we get P as 1.739 kilowatt. Question number 34. A 220 volt DC machine supplies 20 ampere at 200 volt as a generator. The armature resistance is 0.2 ohm. If the machine is now operated as a motor at the same terminal voltage and current but with the flux density increased by 10%, then the ratio of motor speed to generator speed is, answer is option A, 0.87. Given terminal voltage V equal to 200 volt, armature resistance RA equal to 0.2 ohm, armature current IA equal to 20 ampere. Phi2 equal to 1.151. Let Phi1 is the generator flux, Phi2 is the motor flux, N1 is the generator speed, N2 is the motor speed. In a DC generator, induced EMF EG equal to V plus IARA. Substituting the values of VA, IA and RA, we get EG is 204 volt. In a DC motor, back EMF EB equal to V minus IARA. Substituting the values, we get back EMF as 196 volt. N2 by N1 equal to EB by EG into Phi1 by Phi2. Substituting the values, we get it as 0.87. Question number 35. The speed of a 4-pole induction motor is controlled by varying the supply frequency while maintaining the ratio of the supply voltage to the supply frequency V by F constant. At a rated frequency of 50 Hz and a rated voltage of 400 volt, its speed is 1440 rpm. Find the speed at 30 Hz if the load torque is constant. Answer is option C, 840 rpm. For V by F control, Ns minus Nr should be constant. For 50 Hz synchronous speed, Ns equal to 120 by F. Substituting the values of F and P, we get it as 1500 rpm. Rotor speed given Nr equal to 1440 rpm. Slip speed S equal to S into Ns, which is also equal to Ns minus Nr. Substituting the values of Ns and Nr, we get slip speed as 60. For 30 Hz, Ns equal to 120 into 30 by 4, which is 900 rpm. Therefore, Nr equal to Ns minus Sns. We know the value of SNS as 60. Substituting those in this equation, we get it as 840 rpm. Question number 36. A current of minus 8 plus 6 root 2 sin omega t plus 30 degree ampere is passes through 3 meters. Center 0 PMMC meter, a true RMS meter and a moving iron instrument. The respective readings are option C, minus 8, 10, 10 is the correct answer. PMMC reads only DC values. A waveform consists of both AC and DC components. That is A0 plus A into sin omega t plus phi. But for first component A0 is associated with the DC and second is associated with the AC. Hence, reading of PMMC meter is minus 8 ampere. True RMS meter and MI reads RMS value. Hence, RMS meter and MI reading is RMS equal to root of A0 square plus A by root 2 whole square. Equation 1 is only valid for different frequencies. Substituting the values of A0 and A, we get RMS as 10. Therefore, true RMS meter and MI reads RMS value of 10. Question number 37. In a transformer, 0 voltage regulation at a full load is, answer is option C, possible at a leading power factor load. Voltage regulation for the transformer is given by the ratio of change in secondary terminal voltage from no load to full load to no load secondary voltage. Voltage regulation E2 minus V2 divided by E2, where E2 is the no load secondary voltage and V2 is the full load secondary voltage. Positive sign is used for lagging load and a negative sign is for leading load. Hence, voltage regulation can be negative only for capacitive loads. In transformer, minimum voltage regulation occurs when the power factor of the load is leading. The voltage regulation of the transformer is 0 at a leading power factor load, such as capacity load. Question number 38. A three-phase synchronous motor connected to AC mains is running at full load and unity power factor. If its shaft load is reduced by half with the field current held constant, its new power factor will be, answer is option B, leading. In a three-phase induction motor, V equal to E cos delta, where V is the terminal voltage, E is the back EMF and delta is the load angle. With a constant excitation, E is constant but delta decreases as load decreases. So the cos delta is increases. Then E cos delta greater than V, the machine operates at overexcitation, thus operating at a leading power factor. Note: overexcited means E cos delta greater than V. Synchronous motor works at a leading power factor. Normal excited E cos delta equal to V. Synchronous motor works at a unity power factor. Underexcited E cos delta less than V. Synchronous motor works at a lagging power factor. Question number 39. A three-phase, three-stack variable reluctance stepper motor has 20 poles on each rotor and stator stack. The step angle of the stepper motor is, answer is option B, 6 degree. Given number of stack M equal to 3, number of rotor poles PR equal to 20. We know step angle beta equal to 360 divided by MPR. Substituting the values of M and PR in step angle equation, we get the step angle as 6 degree. The last question of this video is 40th one. A single phase 50 kilovolt ampere 500 volt 2 winding transformer has an efficiency of 95% at a full load unity power factor. If it is reconfigured as a 500 volt 750 volt auto transformer, its efficiency at its new rated load at unity power factor will be, answer C, 98.4%. Total winding in 2 winding transformer equal to total losses in auto transformer. Given efficiency of 2 winding equal to 95%, which is equal to 0.95. Efficiency of 2 winding equal to 50 into 10 raised to 3 into 1 divided by 50 into 10 raised to 3 into 1 plus total losses, which is equal to 0.95. After rearranging, we get total loss as 2.63 kilowatt. Therefore, efficiency of auto transformer equal to 50 into 10 raised to 3 into 1 divided by 50 into 10 raised to 3 into 1 plus substituting this total losses in that equation, we get efficiency of auto transformer as 98.3%. Thank you.